Hello everyone, welcome to our channel Everyday Learning. So in today's video of digital logic design, we are going to study a counter with irregular count sequence. And irregular count sequence means that it can move from any number to any number. For example, let us consider this sequence, which is 1, 2, 5 and 7. So what is happening here is the sequence or counter is moving from 1 to 2, then 2 to 5 and 5 to 7. There is not a particular sequence, and then again recycles to 1. So the binary forms are 0, 0, 1, 0, 1, 0, 0, 1, 0, 1 and 1, 1, 1. So the sequence is changing arbitrarily, that is randomly, and there is no fixed stepping up or fixed difference between the two sequences. So we are going to design using JK flip-flop, using JK flip-flop the irregular counter. For this sequence, for example, we need total 3 JK flip-flops. Alright, so at first what we need to do is, this is our step 1, and in this step 1 we determine the sequence of the transition. So we have from 1 to 2, 2 to 5 and 5 to 7. We also wrote down the consecutive binary numbers for the sequences. Now moving on to step 2, we need the next state table. We need the next state table. For this we need at first here present state and then next state, and here we will keep the clock pulses 1, 2, 5, 7. Sorry, this is not the clock, this is the sequence. Alright, now we have for 1, 0, 0, 1, this is Q2, Q1, Q0, and here will be next state Q2, Q1, Q0, 0, 0, 1, and then comes 0, 1, 0, and then it's 1, 0, 1, and finally 1, 1, 1. And we can see from this table that the next state for 1 is 2, which is 0, 1, 0. So 0, 0, 1's next state is 0, 1, 0. And from 2, the next state is 5, which is 1, 0, 1. So here it will be 1, 0, 1. Then we have from 5, the next state is 7, which is 1, 1, 1, 1, 1, 1. And then again 7 moves to its next state, which is 1, and in binary that is 0, 0, 1. Now in step 3 we need the JK flip-flops transition table. JK flip-flops transition table. So Qn, which is the present state, and Qn plus 1 is the next state, and on the right side we'll keep the flip-flop inputs. We have for J and for K. Now the states changes are from 0 to 1, or here again 0 to 1, and we have 1 to 0 and 1 to 1. So we have for change from 0 to 1, 0 x, again it can also be 1 and x. This is basically don't care, I am representing by x. And if the change is from 1 to 0, the flip-flop inputs are don't care and 1, and for 1 to 1 it will be don't care and 0. Now using this table we will determine our inputs for the counter development. We have J2, K2 at first, J1 K1 and J0 K0. We will take the states from here. So we can see that for 0 the change is from 1 to 0. For Q0 present state and Q0 next state, the change is from 1 to 0. And we know for 1 to 0, J will be don't care and K will be 1. So at first we will have here don't care and 1. Again, we can see that for this one, the change is from 0 to 1. The change is from 0 to 1. And from 0 to 1, we have here 1 and don't care. For 0 to 1, we have 1 and don't care. So we'll write here 1 and don't care. In this way, we will observe the other changes and write all the values available here. So the next one will be don't care 0 and don't care 0. Let's see for J1 and K1, which comes from Q1's present state to Q1's next state, which is at first 0 to 1. For 0 to 1, we have 1 and don't care. Then we have don't care and 1, 1 and don't care, and don't care and 1 finally. And then for J2, we can see that the change is from 0 to 0. Oh, this one will be 0 to 0. This one will be 0 to 0. For 0 to 0, the change is 0 and don't care. Again, we have 0 to 1. For 0 to 1, it is 1 and don't care. Then we have 1 to 1, which is don't care and 0, and 1 to 0, which is don't care and 1. So we have got the values for our J0, K0, J1, K1 and J2, K2. Now we can use it in a K-map and simplify to get our simplified expression, which will help us design the logic diagram for the counter. Now I'm not showing the K-map simplification here. I have already done it from before, and I'll just take the equations. So for J0, we'll get J0 is equals to 1. We'll have K0 is equals to Q0 naught. Then we have J1 is equals to 1 and K1 is equals to also 1. Then we'll have J2 is equals to Q1 and K2 is equals to Q1. So these are the pair of values that you can get by simplifying all these using K-maps, and then we can use these logic equations to form our counter. So I have drawn it from before and I just pasted here the logic diagram. So you see here J0 is connected to high, whereas K0 is connected with Q2. Okay, I wrote it mistakenly Q0, it will be Q2. And J1 and K1 both are connected to 1. You can see here high is connected. And finally J2 is from Q1 and K2 is from Q1 as well. Since it is a synchronous one, they all have a common clock, and we get our respective outputs from here, which is Q2, Q1 and Q0. In this way, we can develop the irregular counter. So it is pretty easy. What we need to do is at first determine the counting sequence, then move on to step 2 and draw the next state table. Using the JK flip-flops transition table that I have used here, the JK input values can be easily determined from the next state table, and then simplifying using K-map the inputs of JK pairwise will get different values for J0, K0, J1, K1 and J2, K2 will have more values if our counter is of greater bit size. And finally, using this simplified equation, we can get the logic diagram for our counter that will serve our purpose. So I hope the concept is clear to you people right now. If you have any confusion, feel free to write down below, and don't forget to subscribe to our channel. Thank you for watching this video.